Welcome back to Introduction to Genetics and Evolution. In the previous video, we were looking at this dichotomy between genetics and environment. And what we did in that context was trying to figure out whether or not there's a genetic component to particular trait differences you see, or whether there's an environmental component to trait differences we see. Now, what we want to really do is to actually get this part. We want to say how much do each contribute to particular traits of interest. We want to quantify how much they contribute. Now again, when we're inferring whether genetics or environments contribute, typically the answer is very often both are contributing. In that regard, it's not really that satisfying to just say, yes, there's a genetic component, or yes, there's an environmental component. It's much more satisfying to actually infer their relative contributions. To say for a particular trait, this is something that 90% of the variation you see is genetic, or 90% of the variation you see is environmental. Well, this comes to the concept that we'll refer to as heritability. I'll define that in just a moment, but first, let me go through a couple of quick mathematical concepts that will be relevant to this lecture. Let's talk about mean and variance, please. And I apologize for those of you who already have a lot of statistics background, but I just need to go over this. Now, most traits you look at tend to be variable, that not everybody has exactly the same trait value. So you can use height as an example there. Now, if a trait is continuously variable, right, meaning that you have all these different steps, so something like height, you can be 5 foot 9 inches tall, 5 foot 10 inches tall, 5 foot 11 inches tall, 5 foot 11.5 inches tall. Then we can calculate a mean and we can calculate a variance. Now, many of you are familiar with variance in the context of just thinking of it as the spread of values. And I can depict this. So let's say you're looking at height in the classroom. So let's say this is the height in the classroom. This is saying 5 foot 0 to 6 foot 2. This is 5 foot 0 to 6 foot 2. What is the mean? Well, in both of these classrooms, it looks like the mean is right below 5 foot 7. Okay. In contrast, which one has more variance? And again, if we think of variance just as spread, we see here the graph on the left has a lot more variance in height than the one here on the right, where basically everybody is 5 foot 7. Well, making this more quantitative, the mean is simply the numerical average. That, if you have three numbers, 1, 2, and 3, the average is 2. You sum them all together and you divide by the total number of values. The variance is a spread, or basically how spread out individual measures are from the mean. The calculation for it is this: the summation of all the individual measures minus the mean, and for each one of those squared, divided by the total number of measures. Okay, that's the formal formula for the variance. So if you had 10 individuals, all with height 69 inches, okay, so now let's imagine that's their height. Everybody has height 69 inches and there's 10 of them. What is the mean going to be? Well, the mean's obviously going to be 69 inches. What is the variance? Well, in fact, in this case, there's absolutely no spread whatsoever, because we said everybody has exactly the same height. So the variance would actually be 0 in that example. Let me give you a few others. Here are two sets of measures. Let's say these are, again, heights of people in a classroom and height in inches. And I have the formula here in case you want to refer back to it. So in classroom 1, 63, 65, 67, 67, 69, 71. Those are the heights you see. For classroom number 2, 65, 66, 67, 67, 68, 69. Which one has greater variance? Is it classroom number 1, classroom number 2? Or are they equal? Well, you can probably do this without the math. Let me encourage you to try that without the math. Answer on the next question within the video here, and then I'll show you how to work it out both with the math and just eyeballing. Okay, well, I think eyeballing this is a pretty easy problem. Looking at the spread here, they're both perfectly symmetric, right? But this one goes further out. This one is much more clumped together. So the answer is number 1 definitely has more variance than number 2. But let's try this out numerically. So if we get the height in inches, the means for both are 67. That's just adding all the numbers together and dividing by the number of measures. The variance in this case comes out to 6.66 for classroom number 1. This is taking each individual measure minus the mean and then squaring it, adding all those together and then dividing by the total. So this is 6. This comes to 6.66. For those who are interested in sampling variance, no, I didn't put that in there. For the classroom number 2, it comes out to 1.66. So clearly there's more variance in classroom number 1 than classroom number 2. Well, variance, and don't worry about the math for this right now. We'll come back to the math later. Variance, think of it, again, just as the spread that you see. As the variance is larger, there's more spread. As there's less spread, the variance is smaller. Okay? So what causes this variance in traits like height? Well, let's use this example right here. Let's say here on the y-axis we're looking at number of offspring that have a particular height, and on the x-axis we're looking at height, such that this would be short at this end, and this would be tall at this end. Okay? So we see here, in this particular case, there's some variance in the phenotype being height. That we have some individuals that are on the tall end, some individuals that are intermediate, some individuals that are short. Now with this example, we're looking at two alleles at a single gene that are controlling height. We're assuming there's no dominance to it, and there's no effect of the environment. So that's why these are perfect lines, that if you're little a, then you're exactly that height always. If you're big A, little a, there's more of you, and you're exactly that height. If you're big A, then you're exactly that height. So in this case, there's no effect of the environment, and there's some variance there among the individuals. That variance in this case is all genetic, right? Because we said there's no effect of the environment, so all the variance is genetic. Now what if we saw this? This is still two alleles at a single gene controlling height, and there's still no effect of environment, but we see a bigger difference in height between some of the individuals. In this case, the lower graph here has more genetic variance than the upper graph. Both of them still have no environmental variance, but the lower one has more genetic variance because you see there's this bigger difference in phenotype among individuals with no environmental part, and it's purely controlled genetically. It's controlled by your genotype at the A gene. Now what would happen if we said, well, there's a little bit of environmental variance here and there's a little bit of mush? Well, we might see something more like this. In this case, big A individuals are still intermediate, little a are on average taller, and big A are on average taller. But we have some effect of the environment in here too, where some big A individuals might be almost as big as a big A individual. Some little a individuals might be as short as a big A. But what we've done here is we've added some environmental variance, some effect of the environment. There's still a genetic variance here because there's still a difference among the genotypes on average, but there's also some environmental variance. This is probably the more typical scenario where you have this mix of genetics and environment. Now, the formula that we use for this is very simple. VP, which is the phenotypic variance, so you calculate the variance in height, just like we did before in the beginning of this video. And we say that's the sum of that fraction of the variance that's genetic with that fraction of the variance that's environmental. It's a very simplistic formula that the overall phenotypic variance has a genetic component and has an environmental component. Okay? Now, how do we calculate this? Well, that's the big question. I'm going to show you in this video one mean, and that's using an F2 cross between some strains that are isogenic. In the next several videos, you'll actually see other means for calculating heritability, and specifically what fraction is genetic versus phenotypic. Now, let's say that you're looking at genetic variation in the F2 of a cross, and let's say there's 6 genes for height. Let's start with the very artificial scenario that we know these 6 genes are involved, and you have capital A, capital B, capital B, capital C, capital C. It's just like the example we used a while back. So these are some 6-foot tall people, and this is the exact genotype that's causing that height. And let's say they have kids with these ones that are 5-foot tall. Okay? How much genetic variance is there in the tall parents? Well, we're saying there's none because we have their actual genotype there, and they're all exactly the same. In this case right here, we're saying there's absolutely no genetic variance in the short parents either. Right? What about the offspring? They're all heterozygous. Is there any genetic variance? The answer is actually no, because every one of the offspring has exactly the same genotype. Even though they're heterozygous, even though they have 2 different alleles, there's still no genetic variance in these F1s. In the F2, however, you'll have a lot of variance, some of which will be genetic, because you'll start to get some individuals that are big A, some individuals that are little a, etc. And if you're unlinked, then there's many, many possibilities. And you saw this before with the slide I used earlier. So let's do this cross. Again, we're saying there's no genetic variance in the parentals, in this parental, in the tall parents, or in the short parents. Between the parents, yes, sure, there's genetic variance, but we're not looking at that. We're looking within this parent, or within the F1s. There's no genetic variance. When we see this genetic variance in the F2, right, we see that there's this massive increase in genetic variance in here. We can use that. We can leverage it. Let me show you how. Let's say, for example, in actual height, among the tall people, among the 6-foot tall people, there was no phenotypic variance. This is important. I'm saying phenotypic variance. No phenotypic variance there. Remember, phenotypic variance comes from genetic variance and environmental variance. Since we already knew there was no genetic variance there, if there's no phenotypic variance, then there can be no environmental variance. Okay? So VP is 0, VG is 0, and VE is 0. This is true for all three of those. Now let's add another step here. Let's say there is a little bit of environmental variance. That's okay. I mean, we can say that maybe all these people aren't exactly 6'0", all these people aren't exactly 5'0", but let's say we know they have this particular set of genotypes. In this case, there's still no genetic variance, but there is some environmental variance. You note the environmental variance should be about the same for all three of these. Okay? We're assuming that these are all grown in, say, the same garden, or if they're people, they're obviously not grown in a garden, but you know what I mean. Now, what will happen is in the F2, even though you had a little bit of environmental variance here, but no genetic variance, in the F2 you'll have genetic variance and environmental variance. Well, we can leverage this, because up here, the phenotypic variance, which this you can measure, you can measure the phenotypic variance in the F1s or in the parents, right? You can measure it just the way I was showing you with height, where it's the difference between individual measures minus the mean squared divided by the total number assayed. You can measure the phenotypic variance. In this case, you're getting an estimate of VE. Over here, you can again measure the phenotypic variance, and you're getting VG plus VE. So all you have to do is subtract this phenotypic variance minus that phenotypic variance, and you get VG, right? If you take this phenotypic variance, which is VG plus VE, subtract from it this phenotypic variance, which is just VE, you should get VG, right? Very simple. Well, again, these are the components we have, and we want to know how much is genetic versus environmental. How much is that contributing to the overall phenotypic variance? Well, the fraction of the total phenotypic variance that is genetic is called heritability. So heritability is called VG over VP, or you can think of it as VG over VG plus VE, because that's just synonymous with VP. So this ranges from 0, when there's absolutely no genetic component, to 1 when there's all genetic components. So you can say something, for example, is 90% of the variance is genetic, or 10% of the variance is genetic, using this very simple formula. So let's try this out. Here are some examples. Let's say you manually calculate the variance in the F1s to be 5. So here, this number is equal to 5. Okay. You manually calculate the phenotypic variance here in the F2s, and you calculate that to be 25. Okay. So what is the heritability? Well, I have the formula right here. Heritability is VG over VG plus VE. Well, we know VE, right? VE is 5. And we're assuming the same VE here as over here. We're assuming it's the same. So we're assuming the environment is basically the same in the F1 as it was in the F2, right? So the genetic variance must be what? Well, VE was 5. VG must be 20. So the heritability in this case, heritability is often abbreviated H squared, is equal to VG, which is 20, over VP, and we'll use this one right here, because we're measuring this in the context of the F2 is 25. So the answer in this case would be 80%, or 0.8. Now this may seem like an artificial scenario, because what's happening here is you're starting with lines that you know have no genetic variance. Now, in terms of human height, sure, you'd never apply this. However, this is something that is quite commonly used in the context of, say, crops, where you have this pure breeding tall corn crossed to pure breeding short corn. You want to look at the heritability of corn height, or something along those lines. The same with model organisms like Drosophila, fruit flies, things like that. So this is used quite a bit, but it's not used in the context of, say, human height or anything dealing with humans. Well, how do we deal with things like humans? Well, that's the subject of the next video. Thank you.